Let's pursue our study of open systems by looking at pipes and nozzles. And to begin that study, I'm going to introduce you to the open system energy balance. Refrigerant 134A enters a horizontal pipe operating at steady state at 40 degrees C, 300 kilopascal, and a mass flow rate of 0.6 kilograms per second. At the exit, the temperature is 50 degrees C and the pressure is 240 kilopascals. The pipe diameter is 0.04 meters. Determine A, the velocities at the inlet and exit in meters per second, and B, the rate of heat transfer between the pipe and its surroundings in kilowatts. Let's look at a schematic of this system. We've got a pipe with an inlet we'll call state 1 and an exit we call state 2. There's a mass flow rate of R134A flowing through the pipe, and so we'll take our system as the 134A molecules that are inside the pipe between the inlet and exit. And as always, if there is heat transfer between the surroundings and the system, then positive heat transfer is described as energy being transferred into the system via heat transfer. Let's look at the given data. State 1 is at 40 degrees C and 300 kilopascal, which is 3 bar. The diameter is 0.04 meters and the mass flow rate is 0.6 kilograms per second. Now at the exit, the temperature is a little higher. It's 50 degrees C and the pressure is a little lower due to friction in the pipe. The pressure at the exit is 240 kilopascal or 2.4 bar. It's a constant diameter pipe, so the final diameter is equal to the initial diameter. Let's look at a property diagram so we can visualize this process. Let's look at for state 1. Let's go to the saturation table at 40 degrees C, which is the temperature at state 1. And we find the saturation pressure is a little over 10 bar. But state 1 is only at 3 bar. So state 1 is clearly a superheated vapor. So I'm going to plot it out here in the vapor region. I'm on a PV diagram. And remember, on a PV diagram, constant temperature lines go down to the right. So state 1 is easy enough to locate. It's at a pressure of 3 bar and a temperature of 40 degrees C. Now the temperature at the state 2 is a little higher. It's 50 degrees C, but the pressure is lower. It's at 2.4 bar. And so we can see that it's also at state 2, it continues to be superheated because it's at a higher temperature and a lower pressure. And that increases the specific volume. The specific volume of state 2 is greater than it is at state 1. Let's model this system as an open system operating at steady state. Now, a pipe has no mechanism for doing work, so the power output of this process is 0. It's a horizontal system. There's no change in potential energy, and we rarely regard changes in potential energy for any process involving a gas. They're simply too insignificant. And we are asked to find the velocities at the inlet and exit, and also the rate of heat transfer between the system and its surroundings. So let's introduce the open system energy balance, which I've written here. And let's compare it to the energy balance for a closed system that we're familiar with. Recall that for a closed system, the change in energy in the system during a process is the change in internal energy plus the change in kinetic energy plus the change in potential energy, and that energy change is equal to Q minus W. Now we're going to see very similar terms in the open system energy balance, but the first thing we're going to do differently, we're going to write this open system energy balance as a rate equation. So instead of delta E, we're going to have dE dt, and for any steady state process, properties are always constant with time. So energy is a property. So dE dt will always equal 0 for a steady state process, which is the only kind that we're going to study in this particular course. So we had delta E is Q minus W. Well, now we have the E dt is equal to 0 is Q dot minus W dot. But we have all these other terms in our closed system balance. We had internal energy, kinetic energy, and potential energy. Well, they're going to be included here. And we have a mass flow rate through an open system. And so with the mass flow, we have energy coming into the system, and we also have energy leaving the system. So you can see this first term is the mass flow rate times H1 minus H2. Well, this is mass times the change in specific enthalpy divided by time. So this is when you multiply mass times small h, you get a capital H, and then we're just dividing it by time to make a rate out of it. Now, why enthalpy instead of internal energy? Well, remember, enthalpy is just internal energy plus PV. And so enthalpy includes the internal energy, but the PV is new in that PV is essentially the energy associated with pressure. And since we have pressure to bring the mass into the system and pressure to move it out of the system, we have to include that here. So the internal energy term evolved into an enthalpy term. And then we have the mass flow rate times V1 squared minus V2 squared over 2. Well, that's just the rate of kinetic energy change, and we multiply the mass flow rate times G times Z1 minus Z2, we get the rate of change in the potential energy. Now, this is kind of a long-winded equation, although in most cases we're able to simplify it by removing some terms. In this particular problem, recall that there's no mechanism for doing work, so we can get rid of this power term right here. And also in our engineering model, we said that we were going to ignore any changes in potential energy as being insignificant. So we can remove this term as well. And so now we end up with an equation that involves the heat transfer rate, enthalpy values, and velocity values. So we should be able to find the enthalpy at state 1 and state 2, and the velocity at state 1 and state 2. And once we've done that, the only unknown left in this energy balance is the heat transfer rate. And once again, I'm going to point out that I cannot type a dot over a letter. The closest I can come to that is to use a prime. So this Q prime is actually read as Q dot, and this would be W dot and M dot. Let's begin at state 1 and find the specific volume. I can go to the R134A superheat table at 40 degrees C and 3 bar. And there is no row in that table for 3 bar. I have values at 2.8 bar, and I have a specific heat value from the table at 3.2 bar. And of course, the 3 bar is exactly halfway in between these two. So I'll average these two values, which is a form of interpolation, and I get a specific volume for state 1. Now, we want to find the velocity at state 1, and our continuity equation, simply that the mass flow rate is area times velocity divided by specific volume. I can now calculate the velocity as just the mass flow rate times specific volume divided by area. We have values for all of these. I've got a mass flow rate. We just pulled this specific volume value out of the table. I know the diameter, and the area is just pi over 4 times diameter squared. And I calculate a velocity at the inlet of 38.6 meters per second. Now let's repeat this for state 2. I want to find the specific volume at the exit. And that's in the superheat table at 50 degrees C and 2.4 bar. And I can get that value directly out of the table. And it's 0.10562 cubic meters per kilogram. Now let's find the velocity at state 2. And I can do that by 2 different methods. Let's look at the first one. I can say that the velocity at state 2 is the mass flow rate times the specific volume divided by the area, exactly how we found the velocity at state 1. And I'll put the proper values in for those variables and calculate that the velocity at the exit is 50.4 meters per second. Now there's another way I could do this. The mass flow rate is also the area times the velocity divided by the specific volume. And it's that for state 1, and it's all that so that for state 2. But A1 equals A2 in this. And so I can take this equation of ratios here and reduce it to simply that the velocity at state 2 is the velocity at state 1 times the ratio of specific volumes. Having values for all of those, I calculate exactly the same velocity at state 2 that I did with the earlier method. So we already have seen this energy balance for this problem. And we notice that there's no power output from a pipe, and that being a gas will ignore any change in potential energy. And so I can solve for the heat transfer rate now by rearranging this equation and taking this term over to the other side of the equation where it becomes a negative. And so notice that we have to be careful here. Here I have H1 minus H2 and V1 minus V2, but here it's H2 minus H1 and V2 minus V1. So be careful of which direction this subtraction is taking place. So we need to find the enthalpy at both of these states. So let's begin with state 1, which is at 3 bar. And of course, we don't have that in the table as we found when we were looking for a specific volume. So we'll grab the enthalpy value at 2.8 bar and 3.2 bar. We're exactly in between. So we'll interpolate that as the average. And we get the enthalpy at 3 bars, 284.05 kilojoules per kilogram. So now we need the enthalpy value at state 2, which we can find in the 134A superheat table at 2.4 bar and 50 degrees C. And we can get this value directly from the table. H at state 2 is 294.47 kilojoules per kilogram. Now we can solve our energy balance for the rate of heat transfer. And we've already reduced it to this equation involving the mass flow rate, the enthalpy values, and the velocities at the inlet and the exit. We have all of those values. We have the mass flow rate at 0.6 kilograms per second. We just pulled these two enthalpy values out of the table. And prior to that, we calculated these two velocities. And when we square the velocity, we end up with meters squared per second squared. But we want units of kilojoules per kilogram. And if you go through all the gyrations, you can find that 1 kilojoule per kilogram is equivalent to 1,000 meters squared per second squared. And it takes a little bit of doing to do that. So I just keep this handy conversion factor in my conversion chart. And then I find that the heat transfer rate is 6.567 kilowatts. Now, if I had calculated all these terms separately, I would have noticed that the kinetic energy change was only about 5% of the enthalpy change. And sometimes the change in kinetic energy, even when we have actual velocities, the change is so small that it becomes insignificant and can be, sometimes it just isn't worth calculating or including in our calculations. And in that case, the heat transfer rate would have simply become the mass flow rate times H2 minus H1. Now here, 5% is not completely insignificant. And in the case of 5%, I would have included it, such as we did here. But in other problems, sometimes it's less than 1%. And in those cases, I tend to just ignore the changes in kinetic energy.